So yeah, so thank you. So the title of the talk you'll see is about big data and mobile infrastructure, and it's about what we can do today and what we need to do for tomorrow, for the next generation of applications. So to understand this, it's perhaps important to understand what a cloud is. Okay, and I know people hear all these buzzy terms called cloud. You hear about IBM, and so what I wanted to briefly discuss exactly what is a cloud. So a cloud is basically, you'll see here I have an image of computing equipment. So we're talking about computer nodes and storage that are connected together so they can talk with each other. So what you also hope, so it's about computing and software, it's about computing equipment, but it's also about software that runs on it. How many of you use an external mail provider, like Gmail or Yahoo or Hotmail? You all use a cloud, okay? You may not think so. How many of you use Facebook? Oh, come on. How many of you, I don't buy this. Yeah, you're using a cloud, okay? How many of you, well, never mind, but you're all using a cloud. Now you see here I've replicated this image 3 times. And the reason I do this is a site with, kind of local, and it's called a data center. And a lot of times companies like Google, Amazon, all those guys, they have many of these data centers throughout the world. Okay, they're geographically dispersed. They replicate software. They replicate data. You have no idea where you're reading your Gmail, right? And not only that, sometimes that's replicated. Okay, and then you have to deal with consistency, that sort of thing. So that's a cloud. So what does it have to do with mobile infrastructures? Hello. Oh, okay. All right, it turns out, I suspect most of you have one of these, okay, of some kind. And you download apps, all right? Now, let's pretend, in fact, you saw an example of an app just in the previous talk with Charles's Gluco guide. But let's say, you have some kind of app. Let's say a travel app. You may have Gluco guide. You may have a weather app. So what happens with apps is you download them. Now, these things may seem very powerful. They're probably powerful to some of the first PCs a lot of us had, but they're still limited. And so often what happens is that the software you download, basically it allows you to provide input, to receive output, right? But a lot of times the processing, and you saw this with the example in the previous talk, is done on a cloud. So what you do is you take input, it gets packaged together, gets transmitted. That data representing the request gets transmitted to a cloud. And it turns out, this is a fairly complicated thing, is that you see there I have several types of networks that you have to go through. So think of a network as providing roads, right, between endpoints. And in this particular, it could be between computer to computer, server to server, could be from mobile device to a cloud infrastructure, which is a bunch of computers, right? And the backbone provides is the main roads, and then you may have ramps to actually get there, right? So a lot of you, you take your phone, you've got 3G or 4G connection, and you'll send a signal, your phone sends a signal here, and it goes through this type of network and gets to the backbone, which think of that, that's really the internet, okay? And some of you may be in a Starbucks, you connect through Wi-Fi, and you connect to what's called a local area network, and that will then get you to the main backbone, okay? So now most of you could care less. I know that, right? You just know, here's my app, it works, and you don't really care about the magic too much. But there's a lot of stuff going on underneath that, okay? Okay, so the thing is that there are some limitations to this. This is what we do today. We do it very well, okay? Networks provide paths between endpoints. All right, so it turns out that what happens is you have to determine the path. And there are different links or roads that you can take to get from your mobile device to your cloud. And so the longer the path, sometimes the longer the response time. Now, of course, what can happen is you may say, well, just because something is, there's a 5, however you measure that, and something is 3 may be slower because there's a lot of traffic, and that's true. And a lot of times they determine paths dynamically. It's not always done, up front. But then in the end, a lot of times longer paths often mean longer response times. Okay, that's often the case. Which makes it very difficult to develop applications that are highly interactive or require large amounts of data to be transferred, which is the implication you have with big data, right? The other thing is that there's also very minimal support for any sort of mobile device to connect to each other, okay? There's not really there's some support, but sometimes you may want them to talk to each other, and it's kind of flaky. Okay. So you may say, so what? Okay, things work very well right now. Well, yes, they do, but think about this. There's an anticipation of a huge number of connected devices, a huge growth. And what you see here is, look at this. This is 2003. There were about 6.3 billion people, 500 million connected devices. Note that the number of connected devices is fewer than the number of people. Now, our population will increase by 2025 to 7.6 billion. Well, okay, but look at the number of projected connected devices, 50 billion. Okay, that's a lot more than the number of people, okay? It's already more, actually. Now, you may say that a lot of that growth is going to be because, there may be underdeveloped parts of the world that don't have there are parts of the world that aren't quite up to speed as you might find in more developed parts of the world. Okay, maybe, but part of it is you'll see people actually do projections of growth of mobile traffic, and they'll do it by region, and here is the Americas, right? So it's expected that mobile traffic will increase tremendously regardless of the part of the world that you're talking about. So what's happening? The game changer is sensors, okay? So you have this thing where a sensor is basically a device that can measure a simple physical property, whether it's heat, light, motion, or whatever, okay? And they're becoming very widely available. So one thing is, one of the reasons they're becoming widely available, aside from the fact they've become cheaper, but a lot of it is that they're becoming much more resilient. There's been a lot of advances in material sciences to be able to make them a little bit more durable, so you can just throw them anywhere, okay? So that's one aspect. Sensor prices have gone down. They're quite cheap. Now, buying a bunch of them is expensive, but still, they're much cheaper. They are programmable, and sensors can transmit data. Right, so you can send data over a network if you want to, which a lot of times that's exactly what you want to do. All right, sensors can be embedded almost into anything, okay, into any physical object. You can put sensors in the walls to do monitoring of structure, all right? You can put sensors in cars. You can put sensors in this room to detect motion. Sometimes those are called cameras, but you can do stuff like that. I think some of you've heard with the stuff going on this week with the Malaysian airline that there's sensors in the engine, and they were transmitting things to Rolls-Royce, Rolls-Royce. But the thing is people talk about this as an Internet of Things. So today, when we talk about the Internet, for the most part, we think about computers connecting to each other, and sometimes we think about mobile devices. Right, but now we're saying that because you can have sensors, and because sensors can be put into any sort of physical device, you can put them in lots of things. And so now, instead of just saying it's an internet of computers and maybe a tablet, it's now about an internet of things, right? I'm sure some of you might have heard the buzzword, but that's what they're talking about. And so now lots of applications can pop up, right? Smart buildings, medical, military, industrial, commercial, traffic management, environment monitoring. Some of that may all come up in together. Then you need to communicate with each other. For things like medical, you can, patients can be monitored. Their vital signs, you can send them home earlier. And some people would say you get better quality of life that way. But there's a lot of things going on there. So a couple of things. So I'm going to highlight a couple of problems. Okay. So here is smart cars, and so one of the things you might want to do with a smart car is that you may have sensors to see if a person's actually paying attention. There's actually a project at Western Computer Science working on that, where you see if they're actually paying attention, and if they're not, and they sense that a person is crossing the street, then you may want to have the car stop automatically, before that person moves on, or prevent them from moving. Okay, so you may have multiple sensors that need to talk to each other, right? And that's not well supported, right? They need to be able to talk with each other. So they're kind of infrastructure. They're not necessarily part of what we consider the traditional internet, right? So you need communication protocols for that, all right? So that's just one application. Of course, you may want to have sensors could perhaps be used to determine if cars are too close to each other and so they don't collide, right? So you may want sensors to be able to talk with each other. And you want that to be seamless, okay? Now, in a big city, smart city, you can have lots of things going on. You may want to be monitoring the structure of buildings. So if there's an earthquake or something, you may want to see, okay, is this building in danger of collapse? So, as an example. But there's lots of little things you could be doing. But one of the things is, you think about this, is that you may now want to do things like, we talk about sensors in cars, right? Now, if there is an accident, you may want sensors to be able to transmit something to some remote service, which could then suggest to other cars alternative paths. The reason you want to do that, sensors have limited computing power, so you may actually want information to be transmitted from multiple sensors. Or if there's a disaster and you've got some sort of flooding taking place, okay, you then may want to do something along those lines. Right, you may want you may have flooding damage. You need data from multiple sensors to sort of pinpoint where the flooding takes place, and then you may then want to be able to put out warnings for that. So there, you may want to be transmitting data to some sort of cloud or server, and then it's able to do things. Okay, it's able to do some sort of analytics. So now that infrastructure I just told you, it's not going to be good enough. It was designed really, designed to support this sort of communication, where you basically got a device, it's connecting through whatever networks to get to a cloud. Now, you got to add sensors, okay? And those sensors, you need to be able to collect sensor information for analysis, and sometimes it has to be real time. And I just told you that if the paths are too long, right, it doesn't work very well. So that's why it's difficult to do real time, to do very highly interactive applications. The other thing is, I also just told you that sometimes we want sensors to talk to each other. That's also not well supported. All right. So what happens today, just to give you a quick thought, is today we do, you've probably heard the terms 1G, 2G, 3G, 4G. Right? Those things don't well support that communication between sensors. Right? They're very good at supporting between sensors or mobile devices to that tower, and then you go off from there. You're good for that, but that's not the only thing we want to be able to do. We need more communication, better communication, more seamless communication among what people are now calling the Internet of Things. Right? So basically, we just want to be able to connect any device. And we want to do device to device, device to any sort of device to machine, machine to machine sort of communication to be able to support the new and exciting type of applications there. So last slide is that, you also want to move basically computing to data. Right, as opposed to moving data, you want to move computing a lot closer. And there's a lot of research challenges with trying to do that.
Okay, a quick question for Hanan or Serguei. Is no one anxious to know whether your mobile device in your car are going to get together and report you for distracted driving, issue the ticket.
Wow, that's maybe when I stop driving.
Yeah. The good news is you'll be able to pay for it with those same devices.
Yeah.
Okay, thanks, Hanan and Sergei on that. So, Rhodri, Cusak. So Rhodri is from as associate professor and researcher in the Brain and Mind Institute, and he's been at London for about 2.5 years, coming from Cambridge, and he tells me that he has not yet warmed to our winters. I haven't told him yet that this one's been particularly harsh. Yeah, it's trial by winter here. He's going to talk a little bit about his work on artificial intelligence, in particular artificial intelligence. So it's not a typo, and we'll see what that means.
Can you hear me now? Yeah. Okay, good. So this is a a bit quieter. This is a collaboration with, so I'm Rhodri Cusak, collaboration with Chris Meyer from the Department of Film Studies. And yeah, for those of you that were hoping for a talk on expert systems, you should read the double artificial in there. So what I'd like to, the case I'd like to make to you to start with is that, you know, we've got this kind of continuum for big data. So some data, you know, for whatever reason, there's too much noise or there's just not enough signal in there. It's trash, and it's always going to be trash no matter what you do to it. Now, other kinds of data, you know, they're kind of rich pickings. We know exactly what we want to do, and we'll just run that analysis. Well, hey, free lunch. But it probably isn't a free lunch. There's no such thing as a free lunch, because if that data is easy to extract, then somebody else will have already done it, and it's probably not going to be very interesting. So what I'd like to suggest to you is the gold lies in the middle here. It's the data that we have to work for. We have to do something to work a bit to find the gold. Okay, so for some sorts of problems, we're going to have an automatic algorithm. There'll be some simple algorithm that we can do to give us the answer. So one example, I'm a neuroscientist, so one example of a problem that we might want to tackle is to ask, well, let's try and find the networks in the brain. Let's find brain regions that work together in some way. So what we're going to do is we're going to use Fmri. So we use this functional brain imaging, and this measures brain activity. It takes little snapshots of brain activity. We can do this kind of every half a second. We can acquire a snapshot of a whole brain's activity. And this, you know, this is certainly for me, this is big data. So we get from a single study maybe something between 70 gigabytes up to 2.6 terabytes of data from a single study. So what we're going to do is we're going to get for each point in the brain here, we're going to get a time course of the brain activity through time. And so what we're going to do is we're going to say, well, let's see if the time course of the activity in this brain region changes in the same way as this other brain region here. If they change in the same way, they're probably part of the same brain network. So we can apply, we go off to, you know, some clever mathsy people, and they tell us, oh, you need independent components analysis. So we apply this algorithm. It's kind of, you know, standard off-the-shelf code. We apply this algorithm, and we get an answer that looks a bit like this, for example. This is one of the independent components analysis you get from one of these data sets. And that's this one here is an auditory network, so these are brain regions that respond to sound. Now, so that's great, but is it really the kind of gold we were looking for? So if you look at how much kind of computation time we had to work for to do this, it takes about 2 days per person to process the data. So we've got 700 people. We've got a smallish cluster, 256 cores. Perhaps Rhodri's going to mess it up a couple of times, so we're going to have to do it 3 times. It's basically going to take about 2 weeks of processing time. So I think that this is an example of something where, you know, it's basically this isn't really gold because it's too easy to do. And indeed, you'll find that lots of other people have already done this particular analysis. So this isn't novel. So, and I think it's very rare that you'll have a problem with big data where you know exactly what you have to do, and the only thing that's standing in your way is you don't have the computing power. So just adding computers, that's never going to give you an interesting solution. Or it's really, I mean, it's useful, right? We need those machines to do this kind of analysis, but it's not the answer. We need to do something else. So where are we going to pan for gold? And what I'd like to suggest, the argument I'd like to make to you, is that the answer is we need to add the human touch. We need a human angle when we're looking for these data. So the problem that I just described to you, the sort of processing that I just described to you, we've got this big data, we feed it to a machine, we've programmed the machine with some algorithm, and we then pass on the results to the end user. And the sort of limitations of this, we need some kind of simple algorithm. And sometimes we will know what those algorithms are. Sometimes they may exist, but we don't know what they are. And at other times, there is no simple description of what we're trying to do. We need to have expertise or knowledge or some, you need to put something else in there. So there is no simple algorithm that can solve the problem. And the other sort of challenge of this is that at the end of the day, we run this machine processing. The answer has to mean something to the end user. And so for example, in the example I just gave you, well, we got these networks. I'm showing you one of them. I picked out this one. I told you it was an auditory network because I can recognize it. In fact, we got 39 other networks. Some of them were brain networks that are informative. Other ones were images of noise in the data, and who knows what they mean. So your interpretation is only as good as what you can get out of the data is only as good as the person that's interpreting the data at the end of the day. So, okay, what can we do about this? Well, what we could do is we could take our big data and we could feed it to people. We could have teamfuls, roomfuls of people processing the data, and people are really good at spotting patterns. They can see things, and they have intuitive expertise at recognizing things that they can't possibly describe. They could never, describe it and turn it into an algorithm. But of course, people fatigue and they're expensive, so that's possibly not the solution to everything. So another thing we can do is perhaps we can bring together these two things. And this obviously isn't my idea, but I'm just trying to emphasize this human element. So what we could do is we could take the big data, we could take a little bit of it, we get a load of people to look at it, and we get them to classify the data. We then train a machine we set up a machine learning algorithm so that the machine learns how to emulate what the person's doing. So, what we've done is we've taught the machine how to learn. We haven't taught the machine how to solve the problem. And and the other advantage of this procedure, so it doesn't get tired because we're using a machine, it's cheap, but it acts like we're training the machine to act like a human. And one of the advantages of this is because we've included humans in the process, it's likely that the answer we get at the end of the day will probably mean something to people. Okay, so this is sounding really good, but okay, we've got a problem, which is people are really good at understanding complex data, but only when it's presented in the right form. If you give people, some big field matrices of numbers, they're completely useless at seeing the patterns. But if you can present it as some kind of image or a sound or something, then suddenly they can start to see meaning. So you have to get your data and put it into the right form. Another challenge is what we'd like to do is we'd like to have these roomfuls of people. We don't necessarily want to have super highly trained, very expensive people. We want to use cheap people we want to spread the data analysis around. So we want to, not require great expertise. We don't want to. We want to sidestep any use of jargon or specialized training. So I'm a scientist. I'm not particularly good at making visual representations of things. Just hold that thought because I'm going to say something else first. So along with this, the presentation of data, one thing I'd like to point out to you is often if you can find the right way of presenting data, that's often key to kind of having a new insight about those data. So for example, one of the things I work on is trying to understand how we represent visual objects in the brain. This is something I studied. So what the kind of experiment that we might do, the kind of functional imaging experiment, is we might present a load of objects to people. This is just a little arbitrary collection. And then we're going to record their brain activity. And we'll get some graph of brain activity like this. We actually maybe we're measuring at about 10,000 points in the brain. So we have 10,000 of these graphs. And you can see that, from this just example brain activity, maybe this is the kind of the banana sensitive voxel. So it seems to have some kind of peak just when we show this object here. But it's kind of difficult. Does that tell us something about how the brain represents visual objects? Well, not really. It's kind of hard to understand. But this is a paper, oh, my reference has fallen off the bottom there, but this is a paper from Nico Kriegerskorter. And what he did is, so this is a representation. He's used a method called multidimensional scaling. You take the brain data and you say, let's take the brain's response to each of these visual objects and let's place them down on a two-dimensional page so that things that have the more similar brain response are closer on the page here. So you can see that, for example, all these objects over on the right here, these are all inanimate objects. They don't move. And all the ones on the left are animate objects. So that tells us immediately this brain region is representing animacy. And you can see, the faces are clustering here, and the animal faces are nearby. So again, that's telling us something about this brain representation. And the insight we've got here, was the representation that we made of these data was critical to this insight. And just for your amusement, if you do the same thing in monkeys, if you do recordings in monkeys, you find actually they've got the same representation. So I think this is an example of kind of gold, and it comes from that ability to visualize. Now back to where I was before. I'm a scientist. I'm not particularly good at coming up with these representations of things. So I've been collaborating with Chris Meyer, who's in the Department of Film Studies, and he's a media artist whose expertise is in using moving sound and images as containers for the delivery of complex information. And so what we're trying to do is find ways of representing the data that allows us to kind of tap into people's intuition and tap into people's pattern recognition abilities. We'd like to make sure that it's sort of, we don't require specialist knowledge, so we're trying to engage a broad range of people. And we have an application that is pending, a joint application for an exhibition that's pending in Toronto. Chris is he's not here today, unfortunately. He couldn't make today's meeting, but he's going to be at the meeting tomorrow if any of you are there and would like to talk to him. Okay, so we've decided we need this human touch. We need to present the data in a way that people can understand. Now, where are we going to get the people from? So first of all, I'd like to tell you a story. This is from, many of you may be familiar with this. This is from the 18th century. This was the first, it was a mechanical chess-playing robot. It was a wonder. It traveled Europe for around 80 years. It played many people. It beat, for example, Napoleon at chess. And it was a fantastic thing. Unfortunately, of course, it was a fraud. So inside this machine, hidden away, hence the artificial intelligence, hidden away inside this machine was that there was actually a person, and several grandmasters played within this machine during its tour. Amazon have a service that they called Amazon Mechanical Turk, and the tagline artificial intelligence is actually theirs. They have around 300,000 people who are available to perform human intelligence tasks. So you can post a task up online, you pay, so there's around 50 to 100,000 tasks available at any one time. The typical wage is $2 or $3, and it's a massive pool of people. You can get all sorts of people, and there are many people for whom this is their primary income, or it's an important supplement of their income around the world. So there's a whole economy living in this Amazon's Mechanical Turk. So we've been using it to process the big data sets that we have, or to acquire data sets, in fact. And we've had, so we've used it for things like questionnaires. So, we needed 100, my primary lab's focus is doing neuroimaging of infants. We have trouble getting our infants to sleep in the scanner, so we needed to just do a survey. Let's find out what the sleeping habits of Canadian infants are. So we could either do a whole load of legwork, and traipse around town finding parents, or we just stick it up on MTurk, and 24 hours you've got 100 people filled in your questionnaire. We can test auditory and visual memory. We've had a few thousand people have done tasks for us where we test their abilities, their perceptual abilities, or their memory abilities. We've done tasks with infants. So we tested around 100 infants under less than 1 year on auditory perception tasks. Obviously, we had some help from their parents. We've used it as a sort of processing. So we've used it to identify artifacts in data. So this is an example here of one of the sorts of, this is EEG data from electrical recording on the surface of a scalp. It's actually EEG data we acquired in Africa in newborns. And one of the problems with acquiring data in the neonatal intensive care in Africa is that you end up with all sorts of artifacts. There are people working on their mobile phones, there are strange machines, there's dodgy electrics. So you end up with these artifacts all over the place. So we've been training our MTurk users to spot those artifacts for us and process the data. So our experience with MTurk has been really universally positive. It's surprising. It works surprisingly well. You get a really high engagement from people. People actually care about. It's bizarre when you suddenly connect with all these people that are doing your tasks. They care about what they're doing and they do a good job on the whole. So we get good data. We've got low rejection rates. It's cheap. It costs a few dollars per hour, a few more for babies, and it's flexible, so you can have a task that can last 60 seconds or an hour and a half. People will sit down and do them for you. So I think this is a good potential as a tool to bring the human aspect to big data processing. So just the overall summary. So, panning for gold is gonna take effort to find the effort in the big data. I think the human angle is important. Is one way we can really pull out the gold in our data. I think we'll get new insights from finding ways of presenting data to people in good ways, and I think Amazon's Mechanical Turk has good potential as a tool for this. Thank you.
Any questions?
Elaboration on, for example, in Amazon's Mechanical Turk, how would they be useful to experiment? Like how would they compare, for example, brain images, and what's the assumption? What can they do?
Well, they can do any task. I mean, if you present the data in a suitable way, so say the EEG rejection task here, we're asking them to find, we teach them how to find the artifacts and how to distinguish good brain signal from bad brain signal. We've then got, for each data set will take 50 hours of somebody's time to go through. And if we can train up those Mechanical Turk people, what we have is we have several people do each data set, cross-validate them against each other, and we can find the problem. So it's in that case, it's a resource that's helping us process the data.
I imagine the difficulty in the training, while they're not face-to-face, there's like the documentation must be very...
Well, it depends what kind of, a lot of what, although, there's a bit of a sort of, people are, there's a sort of voodoo skills around this thing that people say they're doing something really complicated, but actually a lot of what they're doing is just pattern recognition. It wouldn't take long if I showed you some of these things. You probably, where's the weird bit in this graph? I've drawn on the grey signal here. But, that you can tell something weird's happening here. And I could train you up with 20, 30 examples. Probably being okay.
Yeah. Is there going to get any information about the demographic of the people who are behind the black box here? Are they like poor people?
They're mixed. So you can see this is a study here. So this is the income. 14% earning more than 70,000 a year. 27% earning less than 10,000 a year. So it's a spread.
But let's say for a specific study that you're doing and you want to report that to...
Yes.
Could you get anything specific for that one study?
Yes, you can ask people anything that isn't... You're not allowed to ask things that personally identify them. So there's a complete firewall between you and them. You can't email them or ask them anything personal, but anything demographic. So, we're doing a music study. We give them a music questionnaire, so we find out how many years of musical training they have. Something like that. You can ask them anything you want. Yeah.
Okay, we'll cut it off there just because we're running a bit short.
Thanks.
Okay, thanks, Rhodri. Sure, okay, we probably won't have time for one question. Oh, okay, go back 10 minutes.